my pleasure to announce our next speaker, Saumya Thomas from APHA, who will be talking about detecting coronaviruses in bats, understanding organ tropism.
Good afternoon, everyone. So today I'll be talking about a preliminary study that was conducted at APHA to investigate organ-specific distribution of coronaviruses in various bat species across Great Britain. So a brief background of coronaviruses. These are a diverse group of enveloped positive strand RNA viruses capable of causing respiratory or enteric infections in animals and humans. So the subfamily of coronavirinae, which is widespread among mammals and birds, as we can see in the figure on the right-hand side, consists of 4 different genera: alpha, beta, gamma, and delta coronaviruses. The causative agent of coronavirus disease, SARS-CoV-2, belongs to the same beta coronavirus group as the SARS-CoV-1 and MERS-CoV that have been responsible for disease outbreaks in human population in the last 2 decades. So why study bats? Bats are recognized as a natural reservoir species for coronaviruses, including SARS coronavirus and sarbecovirus and merbecovirus, and many other wild species are known to be susceptible, potentially enabling spillover into human populations. Bat coronavirus surveillance is essential for early detection, understanding prevalence, identifying potential zoonotic hotspots, and monitoring viral dynamics, which in turn also supports wildlife management and conservation. In the UK, we have 17 different species of bats that are found in and around areas of human habitation. And at APHA, we have a lyssavirus passive surveillance scheme. If any dead bats are found anywhere in the UK, the carcasses are sent to us by bat carers or rehabilitators, or even sometimes members of the public. In 2024, 548 oral and rectal swabs from bat carcasses across various species received via the lyssavirus passive surveillance scheme at APHA were tested for coronaviruses. And PCR and Sanger sequencing confirmed 29 coronavirus positive bats, including pedicovirus, which is an alpha coronavirus in common pastoral bats, Dovington's bats, and Natura's bats. Also beta coronaviruses such as merbecovirus in brown long-eared bats, sarbecovirus in lesser horseshoe bats, and embecovirus in brown long-eared bats. This brings the total coronavirus positive bats detected since surveillance began in 2021 to 83 out of 1,592. However, none of these were positive for SARS-CoV-2. So at APHA, we have been testing oral and rectal swabs taken from bats for over 3 years now, using a 2-step nested pan-coronavirus PCR. These results were presented by my colleague Matthew Bagley here at the conference yesterday, so I'll keep it very brief. As we see in this table, over 1,500 bats were tested and 83 of them were positive, which brings the positivity rate to about 5%. However, because we have been testing diseased bats, it is highly likely that it's not the actual representation of prevalence in wild bats. So the map on the right-hand side shows the representation of the coronaviruses that were detected in bats across Great Britain. So the blue dots represent the alpha coronaviruses that were detected from bats, and the yellow dots represent the beta coronaviruses that were detected in bats across UK. So this is a tabular representation of the bat swabs that were tested last year, as well as a comparison of the oral swabs versus rectal swab results. So this is the list of all the bats that were tested. And as we can see here, there is a trend that the proportion of positive rectal swabs are definitely a lot higher than the oral swabs that were positive. And as you might also notice that the sum of the oral positive swabs and rectal swabs don't tally with the total positive bats because in some cases either the only positive either only the oral or the rectal swabs were positive, and in some cases both swabs were positive. So building up on our results so far from swabs, we also wanted to understand the organ-tropism. We wanted to understand further by studying organ-tropism and why is it important. Understanding the distribution and organ-specific presence of coronaviruses in bat species is critical for assessing potential spillover risks to humans and other animals. And we conducted a preliminary study to investigate the tissue-specific distribution of coronaviruses in various UK native bat species. And these were received via the lyssavirus passive surveillance scheme at APHA and focused on organs such as tongue, salivary glands, trachea, heart, lung, liver, intestine, stomach, kidney, as well as the neck area to include lymph nodes. And the availability of organs depending on the state of the carcass, because in some cases the carcasses were highly decomposed, and obtaining all the organs from these was quite challenging. So here are some of the pics that were taken during our bat postmortem work, these bats were in relatively good condition, whereas we have had other cases where they are so decomposed that all the organs have turned into jelly-like mush. So the bat carcasses that were chosen were chosen based on prior positive tests by pan-CoV PCR for at least one of the swabs, either rectal or oral, and 329 organs processed from 60 different bat carcasses across various species were tested using the pan-coronavirus PCR followed by Sanger sequencing. And the coronavirus was detected in intestinal sample, as well as some of the other organs like trachea and lung, and also kidney in one of the common pipistrelle bats. And Sanger sequencing confirmed it to be a pedicovirus. Coronavirus RNA was also detected from 3 brown long-eared bats, and Sanger sequencing results confirm all 3 of them to be a morbicovirus. Additionally, there was a serotin bat which had come up positive for lyssavirus, and the stomach and lower spine, as well as oral and rectal swabs from this particular bat, were positive for alpha coronavirus. So this is a table summarizing the results from the organ testing so far. So as you can see here, the positive, the red-colored plus signs denote organs from which the coronavirus RNA was detected by PCR and then confirmed by sequencing, and the black dashes denote organs from which the coronavirus was not detected by PCR. And as we can see here, we have had positives from trachea, lung, stomach, intestine, kidney, and spine as well in one of the cases. But there is a common pattern that we can see here, that the intestine is a common factor among most of these bats. So in addition to the organ testing, cell culture work was also done to isolate and characterize coronaviruses from bat rectal swabs that tested positive by the pan-coronavirus PCR. So one of the swabs used was a rectal swab from a brown long-eared bat, which was identified as a morbicovirus, and 2 of the swabs from common pipistrelles as alpha coronaviruses. And morbicovirus was isolated post-infection from rectal swab of the brown long-eared bat through cell culture supernatants. And the cells we used here were the Vero C1008, which are also called as Vero E6 cells. So we've had some promising and encouraging results so far. However, there are also some challenges across the way. So the success of bat postmortem work depends on the storage, sampling, and processing times, which can influence the condition of the carcass. In some cases, the carcasses were sent long time after they were found dead, or in some cases where we weren't able to immediately carry out the postmortem work, they were stored in a freezer, and the thawing from the freezer can also influence the state of the carcass. This work is quite labor intensive, and having a very small team, the time constraints also influence the work. And some bats, such as serotin bats, are handled in high containment SAPO4 ACD3P labs. And if we were to explore cell culture systems, such as ex vivo cell culture systems, they take time to develop. So findings so far support the need for targeted surveillance of organ-specific coronavirus distribution. We're planning to continue the current study to carry out more postmortem work on bat carcasses. And we're also planning to explore ex vivo culture models to investigate infectivity and replication of coronaviruses using specific cell lines as well as air-liquid interface cultures that closely mimic the in vivo characteristics of respiratory epithelial cells, providing deeper insight into organ-tropism. I'd like to acknowledge our colleagues Keela Arrowsmith for bat postmortem training, Megan Golding, as well as the wider viral zoonosis work group, the APHA Central Sequencing Unit, the UK bat carers, rehabilitators, and members of the public, and DEFRA for funding. I would also like to thank APHA and UK-ICN for providing me the opportunity to present today. Thank you so much all for your attention.
Thank you so much. That was a wonderful talk. I think for the sake of time, we have time for one or two questions.
Sorry to hog it. Yeah. Thanks for the presentation. It's really great to see that you're finding so much even in these carcasses, considering how many days, obviously, they've been hanging around and RNA levels probably dropping off a little. One thing, we've been looking at colonies in Gloucestershire, in Lesser Horseshoe, and Young's going to speak about tomorrow. And we see really high percentages of cervicovirus hits in those bats, and some minor changes over the last 5 years that we've been monitoring them. And I see with your Lesser Horseshoe, you got 1 out of 22, but it's obviously very seasonal, the virus infection rates in those colonies. So can you comment on when you're getting most of your carcasses? Because if they're after the pups are born and there's a naive population, that number of hits would probably go up, and your sensitivity for finding those viruses will increase as well.
Yeah, so far we at APHA, we haven't been able to isolate coronavirus from lesser horseshoe bats and greater horseshoe bats. Every time we find any of those carcasses, we do try to test them, but we haven't received positive. The reason I mentioned the sarbecovirus in lesser horseshoe bats was because our colleague Terry, who's sat at the back there, his team managed to isolate sarbecovirus in lesser horseshoe bats while he was working in Nottingham.
Right. Yeah. And which cell line did you use?
Yeah. Yeah, so the horseshoe bats are definitely of interest.
Can I just ask very briefly, you mentioned that certain bat species you're handling in SAPO4. Which bat species with an unknown, uncharacterized coronavirus are you not handling at CL3?
Um,
Hint,
well,
hint.
I specifically mentioned serotine bats and some of the other species which potentially might carry lyssavirus, and they need to be kind of worked with in a ACDP SAPO4 lab. The other work is also carried out in a CL3 lab, but yes, but not in a ACDP3 SAPO4 lab.
Got it. Thanks.
But if we know that it might potentially contain lyssavirus, it makes it more dangerous because we receive the bats through the lyssavirus passive surveillance scheme.
All right, thank you so much.
Thank you.